fact, I just bumped into somebody in the hallway earlier, and we ended up talking about it, and he had a very different perspective on the whole talk than I did. That just happens because we had a collective experience and we're walking around.
This is a talk on 10 problems large companies have with managing C++ dependencies and how to solve them. First, for a little bit of introduction, my name is Augustin Popa. I have been part of the Microsoft C++ team for almost 9 years now as a product manager. As part of my job, I spend a lot of time interacting with C++ developers. And I don't just mean the people that I work with, but also our customers, since we build several developer tools and services for C++ developers, including Visual Studio, Visual Studio Code, the MSVC compiler toolchain, and GitHub Copilot for C++. Product managers on my team use a variety of methods to try to learn about C++ developers, their motivations, the problems that they have, and of course we want to develop solutions to those problems that developers will actually use to be more productive and effective in their work. In the past, I've investigated a variety of problems and observed or heard from developers encountering them. Like, for example, I've seen developers waiting for an installer to finish that's taking a really long time, and so they have to go and look at some cat videos while they're waiting. Or they're just trying to get a basic Hello World program running in a particular environment, and it's just not working. And they end up having to go to Stack Overflow, and they find a solution with hundreds of upvotes, because it turns out lots of people had the same problem. I've heard frustrations about things like performance issues with developer tools. And more recently, I've been hearing from developers about frustrations they're having with managing C++ libraries. For several years, I have been working on C++ dependency management. And I am the product manager for the VC package manager at Microsoft. So this year, I've been talking to C++ developers, particularly at large companies, prizes, about how they manage their dependencies. And in this talk, I will go over some of the patterns I've observed from my conversations, some of the problems they were encountering and how those problems can be solved. I spoke to a variety of companies with many thousands of employees, including Fortune 500 companies. I've also spoken to many internal product groups at Microsoft, as of course Microsoft is also a large company. And this is a summary, I guess, of my findings. So I want to point out that every year there is an annual survey that gets published to isocpp.org. And this is one of the questions that gets asked. Which of these do you find frustrating about C++ development? There are many response options, but I picked the top 5, so that it doesn't get too complicated on the slide. The number 1 top pain point is managing libraries my application depends on. And this has been the case, I believe, as long as this survey has been conducted. In my conversations with large companies, I also found that for large companies, managing libraries is a pain point. Though large companies also have more resources available, more people in particular, and more money that they can throw at the problem to try to come up with various solutions. So there will be a couple of things I'll talk about that large companies can do. I also want to point out build times is a close second. That will factor a little bit into this talk as well. All right, so another question in the survey is, how are developers managing their C++ libraries? A lot of developers are manually managing their dependencies, whether it's compiling the libraries separately outside of their main project and then linking to the project, including the library source code as part of their main build, or just downloading some pre-built binary from somewhere and linking that. But there are also developers that use a variety of package managers. There are several well-known C++ package managers out there. There's also system package managers, and there's a variety of usage across the board. In my conversations with large companies, they're also managing their dependencies in a variety of different ways, sometimes more than one way in one organization or one team. And in terms of package managers, the most popular ones that came up in my conversations were the following: Conan, VC package, NuGet, and then there's custom solution. A lot of companies, especially larger companies, have developed their own internal package management system that they use. And these are usually systems that they've been using for a long time. They're kind of legacy systems, and that they continue to maintain, and their developers continue to rely on. Conan and VC Package are great general purpose package managers. Of course, I work on VC Package, so I'm a bit biased there. But these are great package managers for C++ development in general. NuGet tends to be more popular with MS Build users, especially people who also have .NET code. And if they have .NET and C++ code, maybe they want a consistent dependency management experience. And NuGet is a package manager for .NET, so they can also use that for C++. But in general, Conan and VC Package and custom solutions certainly come up a lot as well. I also want to point out that I gave a talk 2 years ago on why you should use a package manager at CppCon, where I go into more details about the different types of package managers and when you would use the different types. So I won't go into too much detail on that here because I encourage you to look at that talk instead if you want more information on that. I also want to point out the first half of this talk, we'll talk about some problems and solutions that package managers can help with today. But the later half of the talk really gets into topics that you can't just solve by having one tool that does everything. So it's not really a package manager thing. So I'll give you first a preview of the different solutions I'll be talking about. First of all, I'll be talking a little bit about building dependencies from source, but I'll also be talking about downloading pre-built libraries because you probably don't always want to build everything from source every time. And again, build times is the second top pain point. I'll also talk about a particular method to version and manage the versions of your libraries that might not be very well known to many of you. I'll also talk a little bit about how far package managers have come in terms of having a large open source catalog and making it easy to get open source code. And also some of the things that hold enterprises back from adopting open source today. I'll also talk a little bit about what does your build environment look like and really keeping everything secluded and within the internal network of a company and not having to reach out to third-party servers for things too much. And I'll touch on security vulnerabilities, but this is a major topic and there won't be enough time to go into details on it, but there are also other talks on this topic, but I'll touch on this a little bit as well. And also how large organizations centralize common tasks in order to achieve more efficiency when they have many different development teams that want to do similar things. I'll also talk a little bit about SBOMs, which stands for Software Bill of Materials. I'll talk a little bit about reproducible builds, and in particular, making sure that everyone on the organization is using the same compiler and compiler version and having consistency there. And I'll talk a bit about how do you actually make a major change to your development experience. Like, how do you, if you're changing from how you're managing libraries today to something new, how do you break that down and make it easier on yourself when you're a large organization? So first, I want to point out, so throughout parts of this presentation, I'll refer to this code base called, it's an open source project. It's called Cataclysm, Dark Days Ahead. It's on GitHub. It's basically, it's a game. It's a turn-based survival game in a post-apocalyptic world. I'm not going to do too much in terms of editing the game itself as for this, but I'll talk about how the game is actually configured to get the different libraries that it requires. And I will also point out the development environment that I am using. All right, let me switch to. All right, so I have the development environment running in a virtual machine. And I have the game running right now, so this is just an idea of what the game looks like. You can talk to NPCs and have conversations, and you fight enemies and deal with a variety of challenges. But I'm not going to really be playing through the game as part of this. This is just to give you an idea of what it's like. And this is how the development environment is set up. So I have this set up using Visual Studio. There are a variety of ways to actually build this game, but I've done it using CMake in this case. And I'll go into this a little bit more throughout the talk. All right, so if we switch back to the slides. All right, so one big challenge with C++ is that when you compile a binary, that binary isn't really portable. It's effectively unique compared to some other binary that's compiled in a slightly different way. And when you have large companies with many different development teams that are producing individual components that maybe come together to form some cohesive software product, you end up with a very complex dependency graph where many different libraries may have to work together with this consuming application. And each of these components must be built in a very similar way. You have to pay attention to things like what compiler and what compiler version are you using? What is your target operating system and architecture? What are the optional library features you've turned on for each dependency? And in general, you have to take a close look at your compiler flags, and you have to make sure that every part of that dependency graph is compiled consistently. Otherwise, you have problems with ABI compatibility. And a lot of time can be wasted diagnosing issues where something was built slightly the wrong way, and then someone has to go and fix it. In addition, if you're in the business of distributing a library, you can end up with a potentially massive number of possible build configurations that each generate an entirely different binary that only a fraction of your users can actually use. And this is a problem that package manager maintainers realized early on in source packages. So some of the companies I've spoken to consume pre-built libraries. And there are ways to make that more manageable by using something like, for example, package config to identify the right binaries to use. Some companies also try to use semantic versioning, so they can say, okay, well, if we have a major breaking change, we're going to increment the major version. But ultimately, these things can be error-prone, mistakes can still happen, and you can end up spending time diagnosing what's going on. So what I will argue is that the best approach is you want every consumer of a library to have a way to build it from source. There are a few ways of doing this. So for example, you can use a build from source package manager like VCPackage or Conan. This lets you get pre-built libraries, but also build them from source. Not all package managers, by the way, support that. Another approach is to leverage your continuous integration environment, which is probably going to be building everything anyway, and run builds for dependencies, and use the binaries from those builds in consuming projects, like perhaps locally. Thirdly, for first-party packages, you can have teams that produce these packages also share their build instructions with their consumers. And lastly, some organizations have moved towards mono repos, where they try to build as much of their overall code base as possible all at once, using a specialized build system like Bazel to provide some build optimization. There are several benefits of building from source. First of all, if the right binary is not currently available, you don't need to spend time communicating with the owner of that library and waiting for them to produce it for you. A lot of time gets spent in large companies. A lot of the time that gets wasted is not really so much the actual development work, but the communication that happens between teams. And if you have to go back and forth diagnosing what the issue is and getting that other team to produce something for you, that could take a while. But if you have access to the source code and you have a way of building it yourself, then that can often result in a much faster productivity loop. When you have access to the source code, you're also able to view it, edit it, debug it. You can make some tweaks to it if you want to patch something temporarily to see if it works for you. And if you're in the business of distributing libraries, it's also easier and cheaper to distribute source packages than all the possible binaries for every build configuration for all of your users. So at this point, I'll just show how this is configured for the project I'm using. So I have, so this project is configured with VCPackage, and basically there's this manifest file called vcpackage.json that lists all the direct library dependencies that this project needs. And there aren't a lot of them. And there's SDL2 and a few other SDL2 libraries. There's gettext, PD curses, there's a couple of different ones. But there are also some transitive dependencies as well. So in total, you end up building about 23 different libraries. And these get built from source. And the way this is set up is basically, VCPackage provides a CMake toolchain file, and when CMake configuration runs, it calls VCPackage, which then installs the libraries, and it can build those from source. And then once everything is set up and CMake generation completes, then it can build the project itself and then run it, and that's how I ended up with the running project that I was showing at the beginning there. In addition, this particular project has, one of the libraries is actually specifically for this project, so that's what this folder is here for this overlay port. Basically, it's SDL2, has like a special patch that's applied to it on top of what you get by default by just by pulling the version that's available for public consumption. All right, so let's go ahead and switch back. Okay, so remember the second biggest problem with C++ in general, according to the ISO C++ survey, was build times. So if I'm telling you to build your libraries from source, okay, but how long is that going to take? And if you have to do that every single time, it's going to be a problem, especially at a large organization with many different dependencies and many different teams building everything. It's going to take way too long. So really what I'm saying is you should build from source when you have to, but you should still have a way of getting pre-built libraries most of the time. So we need some ways to mitigate the need to build from source too much. And one way to do this is to establish a binary cache. So many companies consume binary dependencies to avoid the long build times. But the question is there still a way to get this benefit while still being able to fall back to building from source if a compatible binary is unavailable? And this is possible with a binary cache. The idea is that you set up a cache that's shared across all of your development environments, like all development machines and continuous integration builds that need access to that cache. And for every single build that you do, you can calculate an ABI hash that uniquely identifies that build. And this is something that VCPackage uses internally so that you don't need to build libraries from source all the time. So in VCPackage, an ABI hash considers lots of things. It considers every file in the source package, the target build configuration, compiler executables, optional library features that were selected, an ABI hash of each dependency in the dependency graph, the version of the build system, the contents of environment variables. If you're using CMake, the CMake toolchain file, textual contents, and certain SDK dependencies, like if you're targeting a specific platform or something, that can also be used in the ABI hash. And essentially, when you want to go and build your project, first you need to make sure all your libraries are set up and that they're compatible with the project that's consuming them. So you calculate an ABI hash for your build. And then you look up each library that you want to make sure is added to your project, and then you check, is this hash in the binary cache? If the answer is yes, you can just download the binary from that cache, and then you complete that acquisition of that library relatively fast. If the answer is no, then you build the library from source, since you would have a way of doing this, and then once that completes, you have a binary for that library available, which then gets automatically added to the cache, which means the next time someone needs to build with the same build configuration, they'll just be able to get it from the cache and do it faster. And you can imagine that if you have this happening, like in a continuous integration system, for example, by the time a developer tries to do it locally, the cache already has everything they could need. And they're generally not looking for things to build from source. All right, so I'm gonna go back to the code base again. All right, so if I run CMake configuration, it's not really going to do much because I've already installed all of my dependencies and the rest of the CMake steps are pretty fast. So it's just going to say, okay, I ran VCPackage, everything looks fine, you already have your dependencies installed. So there's not really much to actually do. But if I go to where my libraries are actually installed, sorry about that, the text is a bit small for me from a distance, but let me switch here. Okay, so I have a folder called vcpackage_installed. So this is the directory where my project is, and under that, under out/build for CMake builds, I have this folder that got generated by vcpackage. So this is where all my dependencies live. So what happens if I just delete this? Well, that means I don't have dependencies anymore. So that's not great. It means I'd have to get dependencies again. But let's see if we can go ahead and do that. So if I run CMake again, and in Visual Studio, I can basically just save the file. If I'm on like a VCPackage file or a CMake file, it'll run CMake automatically because it will realize it needs to do some work. And it's doing some things. It ran VCPackage install again, and it says it's done. So apparently it's already finished. And if I switch back to this, the VCPackage installed folder is back, and I once again have my libraries. And you might be wondering, how is it that it's done so fast? And it's because it didn't actually build any of the libraries from source, because I already have a binary cache with all of my binaries. So all it has to do is reacquire all the files and put everything back in place. So that's basically how that works. And most of the time, that is what you would be doing. All right. Switching back. Okay. So another problem that comes up a lot is version conflicts. So many projects have multiple dependencies, and sometimes those dependencies have their own dependencies. We call those transitive dependencies. But what happens when you have two or more libraries that you depend on, and then those libraries both depend on the same third library? Well, you can end up in a situation called a diamond problem, where those two libraries might disagree on what version they expect the upstream library to be. They may be expecting different API versions of that. And you have to resolve that by essentially picking the right combination of versions for all three of the libraries that actually will work together. And this can come up a lot when you have a large dependency graph. It comes up in the open source world where a lot of libraries depend on each other, and it can come up at large companies which have many internal packages that are depending on each other. So you can't just have multiple copies of the same library with a similar but not the same API in the same build, so you have to find the right combination of versions and have one copy of everything. All right, so most developers, I think in terms of, okay, I need a set of libraries. Here's a list of libraries that I need, and here's a version that I need each library to be. I'm going to set a version for every single library, and I'm going to fiddle with it until I find something that works, and once it works, then I don't touch it. And I rarely update it after that, because then I might have to go and do some more work again. If I make a change to one library, it might break another library and go through this process all over again. So let's throw away this way of thinking for a moment, and let's think of it in a different way. What if instead of one team updating one package, one version at a time, you could track your set of packages and versions as a single version number, which we'll call a baseline. And let's say that within a baseline, all packages have been tested by building them all together to guarantee that they will be compatible with each other. Then when you need to update your packages, you can just instead update your baseline and pull your dependency graph forward in time, which might update multiple libraries, but essentially bring everything forward to a state where you know everything should still work. This is basically how CppCon organizes over 2,300 open source dependencies. A baseline is a Git commit ID. It's a point in time in a Git repo. CppCon has a Git repo. People submit PRs to that Git repo when they want to update or add a library. And basically, there's a continuous integration run that kicks off when you do that, and there are certain conditions for that PR to actually get merged. And when it does get merged, you get a new Git commit ID, which is a new baseline, and any consumers, any users of CppCon can just point their project at whatever baseline they want to use, depending on what combination of packages and versions they want. So the idea is that you get a nice default experience where everything just works. I also want to point out there was a talk in 2021 at CppCon from Bloomberg about lessons they learned from packaging 10,000 C++ projects. I think this is a really good talk. I recommend also checking that one out if you want to see an example of a large company and the challenges that they're dealing with. One thing that I found particularly interesting was that they were using integration baselines to test that a large set of libraries actually are compatible with each other. And they're always doing these builds just to make sure that everything actually still works, so that individual users of those libraries can get something that already works reasonably well. All right, so let's say you have a baseline set up. What do you do when, let's say, a new release comes out for a library? Okay, so what you do is, so in the context of like CppCon, for example, you submit a PR, right? And then when you submit a PR, that starts off a continuous integration run. And in the continuous integration run, it will, of course, build the library and new version that you have and make sure that that works. But it will also build any libraries that it depends on or are dependent by that library. We call these the cones of destruction. And essentially, when you build all of that, we're verifying, okay, if we introduce this library at this new version, are we going to mess anything up in the dependency? And if the answer is no and everything works fine, then the PR gets merged, and now we have a new Git commit ID, and that's a new baseline which users of CppCon can use. So while it takes some time to set up a baseline system, every consumer benefits from not having to worry about stability between different packages as they upgrade. Okay, so let's switch back here. So just to show you what this looks like in CppCon, there's a baseline.json file which lists every single library of like 2,300 open source libraries that are available in the CppCon curated registry, as we call it. Each one is set to a particular baseline version. And there's also a port version, which is basically the build recipe version for like how you actually build that library. And this is a particular point in time. And in the URL, there is a Git commit ID. And this is that point in time. This is the baseline that I'm looking at. And this is, in fact, the baseline that is being used in the project, in the game I was showing you. But there's, if I want to look at a different baseline, which I'll go ahead and copy here. So this is a newer point in time. And some of the libraries have been updated. So in this one, SDL2 image is at version 2.8.2. And in the other one, SDL2 image is, sorry, let me see if I can, okay. All right, it's on version 2.6.3. So it's on the older baseline, it's on an older version. On a newer baseline, it's on a newer version. And there are other libraries that also changed between this time. The old baseline is from around February of this year. The new one is from about 3 weeks ago or so. So a bunch of different libraries have changed. But whichever libraries you happen to install, you're probably not going to install all 2300 for an actual project. But whichever combination of libraries you choose, you get a nice default set of versions for them. So if we switch here, in the vcpackage.json file, there's a built-in baseline. And if I go ahead and update that, and then I run CMake configuration again, it's going to again invoke vcpackage, which is going to go ahead and update that vcpackage installed folder, update the different dependencies. It might update some of them, it might leave some of them alone. And it's done pretty quickly because, again, I have binary caching set up, so I don't have to build everything from source live in front of you. But I had to do that, of course, prepping this project. And it's done, and that's basically how that works. So you'll notice in this file, I'm not actually setting versions for any of these libraries, although I can if I want to. I can still override a specific package and say, I want this version for this package. But even if I don't specify anything, the baseline gives me a default experience that works reasonably well. All right. Okay, so I've been demoing using open source dependencies here. In general, though, I found that companies are finding a lot of challenges with dealing with open source. In almost all of my conversations with these large companies, they were using at least some third-party open source code. But if you count like the total number of packages or dependencies that they have, most of them are still internal or closed source, first-party dependencies. And that kind of makes sense at a large company because, of course, you have many different development teams working on different components of a complex software product potentially, and that results in just a lot of internal code that's being produced and distributed within the organization. But when I drilled into it, I also realized that companies were implementing a lot of logic that you could just get from an open source library, but they were just doing it through their own libraries. So I asked these developers, basically, what are your concerns with open source? So while developers admitted that, well, writing the new functionality from scratch can be more work, it can be easier to maintain because it's all done within your familiar development environment. A lot of open source code needs to be built using specific build systems, which may be different from what you're using. There may be some custom scripts that need to run. You probably have to spend some time reading the build instructions, so going through the documentation and figuring out how to get it. If you have, like you saw in this case, you end up, with this game, you end up with 23 dependencies, even though you might only have cared about a couple. So you have to worry about transitive dependencies and making sure those are set up correctly and that they work with your direct dependencies. So you might end up spending a lot of time basically getting all the open source code working properly. And if you're building everything manually, of course, it can be very painful. We saw that a lot of people are building libraries manually, but with package managers, it's easier. It's going to be easier to do this. There are also a couple other issues that came up. There were licensing concerns, like basically legal risks, making sure you're not consuming an open source package that you shouldn't be using for legal reasons, and also security vulnerabilities. Both of those I'll talk about a little bit later. So at this point, both vcpackage and Conan have very extensive open source catalogs of libraries. Like if you go to their websites, there's vcpackage.io and then there's Conan Center, you can browse all the different libraries that they have available. And there are many of them. We're talking thousands of libraries. And you can build them from source, you can get them pre-built, there are different versions of the libraries available. There's a nice out-of-the-box experience for getting open source dependencies that way. In general, these open source package managers go a long way in terms of dealing with problems with open source, but they don't address all of the problems, like the security and licensing issues that I brought up. So so basically they don't close all of the gaps there. And of course, package managers also resolve transitive dependencies automatically. So you only really have to worry about your direct dependencies. For all intents and purposes, the transitive dependencies are almost invisible when you're interacting with a package manager. All right, so another problem. In my conversations with developers, I saw a pattern where organizations are very hesitant about their employees downloading things from third-party sources. And here are a few scenarios. In some development environments are completely offline. They're segregated. Sometimes they use the word air-gapped. It's basically a build environment where you're not allowed to just connect to the internet and do things. Another scenario could be, well, maybe you're not in a completely air-gapped build environment, but you still just can't. You're not supposed to just go and download things off of the internet to use for your builds. Especially when it comes to open source, you probably have to go through some approval process at your company to make sure that what the code you're trying to use is actually allowed. And there will be some process for doing that. And the third thing is, even if you are allowed to access something from a third-party server somewhere, there's continuity of business. What happens if the third-party server goes offline? What happens if there's a network outage? I think there was a case a few years back where a major library, I think it might have been a JavaScript library, I don't think it was C++, but basically the owner of that library just pulled it one day, and then a lot of companies' systems just went down because there were so many companies dependent on that one library. And so when you're just depending on something from a third-party source that you don't control, you can run into issues like that. So how do we deal with this? Well, organizations can deal with these scenarios by maintaining an internal cache of any assets that are needed for builds to run, such as source code and tools that run at build time. We've also talked about the binaries for the libraries, but then if you're building from source, you also want the sources. So the idea is you initially populate the cache outside of the build environment, and then you have a process to verify that the downloaded assets are compliant with your organization's rules. So you might have to do some investigations or scans to make sure that everything looks good. And then lastly, when the cache has been validated by the company, it can be moved to a location that is within the internal network of that company and accessible to the build environments, whether it's continuous integration or local development. And maybe it's only accessible by authorized users as well. But that way, basically that can be used as the source to get all the assets that you need for your builds. All right, so switching back to this library, or sorry, to this project. Trying to find my mouse cursor. Okay, so what happens if I want to add a new library? So if I want to install an additional library, I basically just add it to my vcpackage.json file. So let's say I want FMT. And then I'm going to go ahead and run CMake again, which runs vcpackage. And you'll notice there's a message here saying there was an asset cache hit, which is somewhere up here. I think it's scrolling through it. All right. Okay, so asset cache hit for FMTlib. So I basically have an HTTP server running locally in this environment. Of course, this could also just be a remote HTTP server, but I'm keeping everything self-contained for this demo in this VM. So you could replace this URL with something else, and essentially that has an asset cache. So what happened here is FMT is not in my binary cache. So I can't just pull the binary. So in this case, I'm saying I've never built FMT before, but I do have the FMT sources in the asset cache. So because I have the asset cache set up, I can still pull that source code, and then it can go ahead and build it, and then once it produces that binary, then it goes ahead and puts everything in the asset cache, or in the binary cache, sorry. So that's basically how that works. So I have a scenario that works offline for both binary acquisition, but also for building source code. I also want to point out that I'm not connected to the internet, and I haven't been connected to the internet at all in this build environment this entire time. So everything that I've been doing has been just happening locally. Normally, when you're using like a package manager to get open source code, you'd think, okay, I'm going to connect to a GitHub repo to get the source code, or SourceForge or something. But for a lot of organizations, you're not allowed to do that. The IT department will block you from doing that. I know that's happening at Microsoft, for example, where we can't download from certain URLs. We're just not allowed to do it, so we have to have a different way of doing it. Okay. So, next problem, security vulnerabilities. So I mentioned that I would touch on this a bit. One of the big concerns that came up in a lot of my conversations with large companies was, especially with open source code, but it's a broader problem than that, is security vulnerabilities. And when you are using more and more open source code, you're increasing the effective attack surface that you have to deal with. There are, of course, lots of well-known examples of third-party projects that have had some security concerns. It's been in the news a lot. There have been lots of headlines. In particular, memory safety issues are very common. And there's also been interest from regulators in doing something about this. And of course, it's a problem very common, particularly with C++. There are lots of CppCon talks that go in depth into this topic, so I'm not going to go in depth here since I have a few other problems to go through. I will point out that my colleague, Jim Radigan, has given a couple of talks on the topics like memory safety, as well as some of the solutions that I talk about here. And I'll reference them shortly. So what are some things that you can do? You want to have, as an organization, you want to have a strategy for vulnerability monitoring, prevention, and response. So one thing you can do is you can review public CVE databases like the GitHub advisory database to find out if there's a new vulnerability that is being communicated about. And then you can develop ways to basically scan your code for references to vulnerable packages. In general, you also want to run static analysis and dynamic or runtime analysis tools on all your code, whether it's open source or not, whether you know about any specific vulnerability or not, because you might find things by doing that. So in terms of like dynamic analysis, things like sanitizers help a lot. Address sanitizer, for example, Jim Radigan gave a talk on that as well, or possibly a couple of talks. And in addition, fuzzing is also something some companies do, where you basically run your program with many different random inputs to see if something goes horribly wrong with one of those inputs. This often will happen in the background, maybe as part of a continuous integration process. This is another way to find some issues. And in some cases, you might have companies that have perhaps third-party code that is checked in as part of their repo of a particular project. And in that case, you might have to develop something more sophisticated, some kind of tool that can scan all of your sources and determine if you're using anything that has a percentage probability match to well-known like third-party code. This is a lot more complicated to set up, but it is something you can do to identify if you are in that situation where you're using something like that. In addition, you want to make it as trivial as possible to update your dependencies if there is a problem that gets identified. You want to be able to respond quickly. Track third-party code, in particular, as explicit, separately linked packages if you can. This makes it easier to swap them out, or to change the version if something goes wrong. You can have scripts that automatically generate PRs for different teams in your organization to update vulnerable packages. This is also something GitHub does for a lot of projects, where they can automatically generate a PR and say, hey, you're using a vulnerable version of a library. Here's a PR to update it. And if you require all the devs at your company to use a consistent dependency acquisition experience, it's easier to basically diagnose any issues that developers are running into when they're trying to move quickly to the new version. It's easier to give them advice and support them through that process. If everyone is doing something different, then it's harder to give advice that is helpful to them. And of course, we talked about how for a lot of companies, they don't want to be reaching out to the internet or some third-party source to download the assets they need to run their builds. And so if you have everything that you need for your builds and all your dependencies that are self-contained within your organization's firewall, and you have access to those actual packages, you can just block the packages that you don't want your developers to use anymore. So you can have a way of doing that. All right, so as organizations grow, it gets harder to manage C++ dependencies, since all the problems we've talked about basically also scale out across many different teams and many different projects. You might have lots of different teams that are contributing components that other people depend on, and they may have to communicate with each other a lot to figure out what one team needs to produce for another team. I mentioned that communication can be one of the slowest parts of dealing with a large company. There's a reason large companies tend to take a while to really make a major change or work on a really major product because there are many different teams that are involved in that, and the communication part is hard. And you can also end up with just many teams, each trying to do their own thing. But if you look at the different teams, they may be doing similar work. So for example, teams may be individually figuring out how do we produce and distribute our libraries? How do we make sure we're compliant with the rules established by our organization to avoid legal and security risks? What documentation do we need to write about how other people can use the libraries we're producing for them? And of course, if we have different teams that are each producing a component and all these components come together, and you have this large software project or product that is the sum of all of that. If one team messes up somewhere and does something wrong and builds something the wrong way, you have your ABI instability issues, you have your version conflicts. It's harder to really manage that when every team operates in a silo and does what they are specifically interested in. So in my conversations, I've noticed that the large companies are increasingly centralizing common tasks. And in general, if you've worked at a large company, a lot of large companies will have an engineering systems team or some kind of team that is basically responsible for making sure that all the developers at that company have a really nice experience. They have consistent processes for doing things, and they know where to go to get help. They're all compliant with everything they need to do, and it just keeps everything simpler, so each team can just focus on their core work and not have to spend too much time with the additional overhead. So this central team, in the context of managing dependencies, can perform several different tasks. For example, they may be responsible for maintaining any third-party packages that you have, like for example, open source packages. And they may also provide some support for first-party packages that are in that ecosystem, although usually whichever team is producing the first-party package is also the one that effectively owns it. But the central team can also provide some supporting functions there. The central team may be responsible for approving new open source dependencies. You may have to talk to them to say, hey, this library we've never used before, I would like to use it. What's the process for that? And they'll go through the process of validating it for compliance and producing some sort of package that you can use. And remember I mentioned that some companies have their own internal package management system. And some companies are also using one of the open source like public package managers that are out there. Well, the central team may be responsible for how you use the package management and the package manager and the workflow associated with it at that company. So they may be responsible for that. And a big benefit of centralizing some of these efforts is that you can enforce some consistency across your whole organization. You can have common package formats, a common storage system and distribution system. You can make sure you properly authenticate users and whether they should actually have access to read or modify packages. You can verify ABI compatibility and establish versioning baselines at a central level where you have a big picture perspective of everything that is going on. Individual teams would have difficulty doing that because they're not really seeing the overall dependency graph for the whole organization. They might just be seeing the things they're directly connected to. So the central team can help running these kinds of integration baseline builds and making sure that everything still works for everybody. Documentation. I know at Microsoft we love wikis. We have lots and lots of articles that have been written by different teams working on different tools and processes that engineers across the company are using. And over time, this has built up into a large database of information. So if you're doing software development at a company, you can go there and find everything that you need for your work. And that includes for dependency management. And package consumers can have one consistent way of consuming dependencies. And again, that helps when you need to provide support to them or when they have questions about something or are stuck on something. If everybody is also doing the same thing, it's easier to actually be helpful to them. All right, so another thing that large companies increasingly have to deal with is auditing. And they have to deal with the fact that they may have many projects. The projects may be very large. Those projects may have many dependencies. Can they even track them all? Can they even build a full dependency graph? Can they understand what the risks are with the way their environment is set up? And there are some scenarios that can come up here. Maybe companies will want to know, hey, does our product depend on something with a known licensing or security risk? Maybe we have an important customer like the US government that is now requiring us to be transparent about everything that goes into our software. It's a bit like the ingredients list on a product at the grocery store, right? If you go and you pick up the box and you look on the back and it tells you what actually goes into that product, and there's a reason that that information is provided to you, because it is useful to know that. And increasingly, we're starting to see this for software products as well, especially these large software products with many different components. And so the topic of software bill of materials comes up. Especially for third-party dependencies, you'll want to organize them and list them as individual named packages if you can, have a way of really being able to identify them and know where they are and how they're being used. And if you can, produce a software bill of materials for your product that summarizes basically all of the dependency relationships there. There are two common formats, SPDX and CycloneDX. I will defer to the US government for the definition, because I like this definition by the Cybersecurity and Infrastructure Security Agency, which defines a software bill of materials as a formal record containing the details and supply chain relationships of various components used in building software. These components, including libraries and modules, can be open source or proprietary, they can be free or paid, and the data can be widely available or access restricted. And they also explain the benefits of SBOMs that apply to both software suppliers and consumers. So of course they help with things like identifying, quantifying, and mitigating risks with licensing and security vulnerabilities. And they can also help you lower operating costs if you realize you have a dependency on something that is not used very much, but it adds a lot of cost to your build. Maybe there's a way you can just pull it out and not have to use it anymore. So there are things like that that you can do. And when you have a big picture perspective of your dependency graph, that really helps. So my last switch to this project, I'm actually just going to so back in the VC package installed folder, I'm going to go under where my libraries are built, basically. I'll go under share, and these are all the different libraries. And remember, the manifest file had only a couple, but this is everything that ended up getting installed. So I can go under, let's say, SDL2, and look, there's a VC package.spdx.json. So every single library that's produced by VC package just comes with one of these now. And it's an example of an SPDX file. So this is basically what it looks like. I think it's a little, the version of this file is a little outdated at this point, but this just gives you an idea. And there are different tools you can use for combining these files together if you have files that are only covering some components of your software product. And there are tools for producing these as well. But I don't go into them in this particular talk, since we need to keep moving here. All right, we're on number 9. So I talked a little bit about, in the intro, about how reproducible builds are an interesting topic for companies. Package managers can really help when you're getting your libraries and you have this manifest file where you declare your dependencies. And you know that you can also declare the versions that you want of your dependencies and exactly how they should be built so that you get the right binaries. And then you can check in that file to source control. And basically that's just going to live there forever. If somebody goes in and checks out that project 5 years from now, they should be able to get the same set of libraries built exactly the same way, just through the package manager following the instructions in that same manifest file. So unless you change the manifest file, you get reproducibility. But there's a lot more to build reproducibility than just your libraries. What about your build tools? What about your compilers, for example? There are lots of different issues that can come up, especially large organizations, again, where you have these many different teams doing things. Maybe you have 2 teams that are contributing components to a common application, but they built their components with different versions of the compiler. Maybe one team was trying out the new version, didn't realize they were on that version, and now, well, we have a problem because we might have an ABI incompatibility between these 2 components. Alternatively, maybe a developer tests a change locally. Everything looks fine. There are no errors. They pass all their tests. So they go ahead and push that to their continuous integration system. They queue up a build. But then their continuous integration system complains and says, well, actually, I built it a bit differently than you. And when I built it, I didn't get the result that you got. I got an error, and there's a problem with it. And the developer realizes, oh, I hadn't actually built it the way I should have. They have to go back, fix the issue. then go and queue up another CI build. And basically some time just gets spent going through that. It's also very easy for someone to just put the wrong flags, the wrong compiler flags, and you get something different than you intended to. Or maybe you built a binary and then you deploy it to production, but it was actually built the wrong way, and then you have to go back and fix it later. And that's even more painful to deal with. So, of course, at large companies, you can't really afford to be dealing with this too often. It's going to end up costing you a lot of time and resources, and it can just be problematic to deal with. So companies are establishing basically a company-wide policy for what build tools and versions you can use. This can also apply to package managers, like everyone's on the same version of a package manager. And remember, if companies are also working within an internal network and you don't just download the tools and assets that you need externally, they can restrict access to any other tools. So they only offer the tools that you're supposed to be using. In addition, companies are increasingly building in container environments where you set up images for the different types of builds that you want that are already pre-configured with everything you need, so that there's less room for error for individual developers that need to run builds. And then, of course, you sometimes want to update your tools. You don't want to stay on the same compiler version forever. You probably want the new C++ features that are coming out. So how do you do that? Well, if you're just working on a small project, it might not be that big of a deal. But if you're working on a large company with many different components and large projects, it is a very big deal. It can take you many months or even years to just move your compiler forward. And we've seen cases of companies that are still on C++ 11, for example. So you have a process in place where you can move at least as efficiently as you can while still allowing enough time for your teams, your product teams, your development teams to actually test the new version. So in practice, you might be working with two different versions of a compiler. Maybe you have the version that builds things for the production environment, which is the older version, and then you have a newer version where you're still testing it out. And individual teams may be going through a process where they're trying to see, okay, if I build with this, what are the errors that I get? What are the breaking changes I have to deal with? And they have to spend some time smoothing out the rough edges there. So that process can take time, and it's a fine balance of figuring out like how much time do teams actually need while we're still asking everybody to move forward at a certain cadence. So you want to allow enough time for that the testing, basically. All right, so last problem. Making big changes to your development environment, especially at a large company, is hard. It is not something that you can just trivially do, and it's you meet a lot of resistance, really, even when you propose doing something like this, especially when you have these many different teams and projects that are involved. There's a fear of breaking builds and having to clean things up. I've been in meetings of multiple developers on a team where one developer is really excited about moving to a new tool, and there's always the more skeptical developer that's also on the team that's saying, there's no way we're going to do that. We've been on this tool for 10 years. It's going to take us another 10 years to move to a new tool. We're never going to do this. Our management will never approve this. It'll never happen. So you always have these kinds of situations that can occur. So the timeline can feel extreme and unrealistic. And it can be difficult to also cost, like what is that migration experience going to look like? And again, managing libraries, very painful and it can be very difficult as well to change how you're currently doing it. So the strategy here is going to vary for each company. I can't give specific advice for everybody, but I'll try to give some general guidance. With any large problems, you want to break it down into a series of smaller steps. And ideally, you want those steps really to be milestones where you get some kind of a win at each milestone. So even if you don't make it to the end, you've already gained something just by moving to the next step. This can help motivate teams to actually make progress. It helps with getting management approval to move forward with the change, because they'll know even if we have to cancel it at some point, we'll still gain something from it. And it just makes things easier. So I'll just give an example. So let's say you're moving from manually managing your dependencies at a large company. Maybe you have some checked in source code for your dependencies as part of your main build, and maybe you also have some libraries you are building externally, but then you're linking it, but you're kind of doing it manually. And let's say you want to move to a package manager. So if you break it down into steps, well, maybe step one is the company develops a tool to scan your source code repositories for references to open source. This can help you identify legal and security risks if you're using something that maybe isn't going to work very well for your company. So even if you just do this step, you're already gaining something. Then maybe step 2, okay, you've looked at these different usages of open source by different teams at your company. You pick a team and you say, okay, you have some free time, you have some free engineering capacity here. Why don't you work on moving your open source dependencies to the package manager? You can develop a proof of concept and then tell us about it, tell us how it went. So that project can then benefit from the new system, and that team will learn from that experience. And it might take them a while because they're the first team doing it. They're the trailblazer. It could take them a while, but then once they get to the end, they'll have a list of insights they've gained that they can share with other teams. And then through word of mouth, they might talk to other teams. Other teams get curious. They see that it worked out well for them. So they start moving their open source dependencies. And over time, you end up with many teams that have moved their open source dependencies and get the benefits and the features from this package management experience. And eventually, the top level management realizes, well, we have lots of teams that are doing similar things. Maybe we can centralize some of these efforts and have a central team that's responsible for maybe package storage, distribution, and some common documentation for dealing with this package manager and the packages internally in this organization. And that reduces the time the individual teams are spending dealing with this whole workflow. And eventually, okay, we're doing really well migrating open source dependencies. And of course, package managers provide open source packages you can just start using. You just have to go and validate them and make sure that they're compliant. But let's start moving our internal libraries to the package manager as well, which requires creating new packages. So they can start doing that. And now you have more libraries that are benefiting from those features that the package manager provides. And eventually you hit a critical mass where lots of packages have been moved to this experience, and then eventually the company management can say, okay, I think we've learned enough that we can, and we built enough documentation for everybody that we can go ahead and say everybody's going to be moving to this new experience. If you haven't already, here's everything you need, here's all the documentations, here's who you talk to get help, and here's the timeline that we'd like you to do it by. And then that's how you basically get to the finish line. So in summary, I recommend if you're consuming libraries, have a way to build them from source. But usually you should be just getting the pre-built binaries. If you can validate that those binaries will work with your project, building from source is kind of the fallback. Organize your dependencies and versions into baselines and upgrade your baselines to make things easier on yourself in terms of dealing with your dependency graph. Use an open source package manager to save time and effort. Create an internal asset cache for everything you need for your builds. Develop a vulnerability monitoring, prevention, and response strategy and any associated tools and workflows for that. Centralize common dependency management tasks, and this is also a way to enforce consistency across your organization. Organize your dependencies into coherent packages and start producing SBOMs. And establish a global toolchain policy where everyone knows they're supposed to be on a specific compiler version, and then also building containers to avoid common errors. And break large migrations down into smaller milestones with a win at each step. All right. If you work at a large company, I think we would all love to hear your story. I mentioned Bloomberg gave a talk a couple of years ago I thought was really interesting. I think we'd all welcome more talks at conferences, or if you don't want to do a conference talk, you could do a blog post, you could start a thread on Reddit, whatever works for you. Share the insights that you've learned in your own experiences. Because again, managing libraries is still the top pain point for C++, and it's still a big pain point for large companies. So there's a lot we can learn from each other. I also want to point out I'm also publishing some blog posts on the C++ blog about how people can be using VC package to make their lives easier at large companies. If you're also a large company, you have an interesting story to share, let me know. I'd be happy to work on a blog with you, blog post. We have some other Microsoft sessions as well at CppCon. There was one yesterday, which I guess you can catch on YouTube now whenever it goes up. So you think you can hash. On Thursday, we have a talk for Visual Studio Code if you're a user of that. And on Friday, we have a talk on Visual Studio and what's new in these tools that you can also check out. And we also have a booth just down the hall. Microsoft booth, come by anytime. We're here through Thursday. So tomorrow and Thursday, we're still there. You have a chance to win swag. We'd also appreciate it if you take our survey. This helps us learn what we can do to make better developer tools and services for you C++ developers. And yeah, it's an opportunity to ask any questions and connect with us if you want to chat about anything. And we have a bunch of swag that we're giving out as well. And that's it for my talk. I think we're almost out of time, but I'm also happy to, if there's no time for questions now, we can also talk outside afterwards as well. Thank you. Yeah, we have 45 seconds left, so we might have time for a quick question, but otherwise, we'll probably just meet outside.
Common package specification for
Yep.
with CMake. Are there any efforts from your side to sort of
Yeah, we've been
accelerate the adoptability of it?
Yeah, so we've been involved in some of the conversations around the common package specification. I've been busy the past couple of months. I haven't been keeping up with some of the meetings, but I've gone to some of the earlier ones, and it's interesting to see the development of it, and we're following it. But we haven't done as much as I think, for example, JFrog has been doing. They gave a talk yesterday on it. But it is something we're closely following and keeping an eye on. But yeah, we don't have any commitments yet beyond that.
Thank you.
All right, so we're out of time. I'll happy to take any questions outside if you have any.